Hi, can you approximate a function at any point, say x equals a, if you know the value of the function at that point along with all its possible derivatives? That's what Taylor series does. Using the fundamental theorem of calculus, you can write a function as the integral of its derivatives, and if you have limits on the integral, then we get this as the difference of function's value at any point x from its value at a. On rearranging, we get our most important equation 1, which says a function to be sum of its value at a with the integral of its derivative from a to x. The second term is going to be the core of this whole derivation. Using this, we can write the derivative of f at any position x to be sum of its value at a with the integral of second derivative from a to x. If we throw this expression for first derivative of f inside the first equation, we have two terms inside the integral. The first term, being a constant, has integral as derivative of f at a multiplied with the difference of limits, which is x minus a. The second term inside the double integral can be expanded using our equation 1 as the sum of second derivative at a plus integral of third derivative of f. As the first term is a constant inside the double integral, so the constant would come out and the first integral gives x minus a, which when integrated again gives a square of x minus a divided by 2 factorial. So we get the following equation, where our new offspring is a term with second degree polynomial multiplied with the second derivative of f at a. Similar to the process before, we can expand the third derivative of f as being the sum of value of third derivative at a with the integral of fourth derivative of f. Since the first term is again a constant and being integrated thrice, this time can simply come out of the integrals. The first integral gives x minus a, second one gives x minus a square over 2 factorial, and the third one leaves us with a cubic polynomial. So the new baby in our equation for f is a term with a cubic polynomial multiplied with the third derivative of f at a. Note that the last term, which now has 4 integrals, is like a mother term, which keeps on giving birth to newer and newer terms with increasing degrees of polynomial each time you expand the term inside. This whole is the Taylor series at the end of the day. Now there is something to observe. If you see the Taylor series again, you would notice that the function f is being approximated as the sum of its value at x equals a summed up with all the possible degrees of polynomials passing through a. In conclusion, we can say that any function can be decomposed as the summation of different degrees of polynomials passing through a.